you do not need to do calculus or memorize every attention equation in a transformer layer. In this video, I'll cover the exact depth and breadth you should know to work well with LLM, to make them your companion, to be the smart engineer in the room, and even to clear interviews. This is at most what's actually expected of you, not less. It gives you the confidence to enter the room too, and I have felt the difference. An LLM on its own does not build an agentic system. The model is the core that makes the agentic experience possible. But the system around it is the real work, and that's what we'll design later in this series and what gets you through those agentic system design interviews. So today it's about the basics.
Hi, I'm Ishween Kaur. I build agentic AI systems in production, the kind that have to survive real users, not just look good in a demo. I've also sat on both sides of the interview table for agentic system design. Here it's going to be no hype, no gatekeeping, just the real building blocks with production experience and how to talk about them when it counts. Let's get into it.
Part 1: How an LLM behaves. At its core, an LLM is a next token predictor. You give it a text, it outputs a probability distribution over every possible next token, samples from the response it gets, append it to the response, and repeats it. That's it. The intelligence is emergent. It falls out of training on a vast amount of human text that it is trained on. Now, how it's built, the model starts random and output gibberish. It trains on trillion of examples with only one objective of predict the next token. Every time it's wrong, backpropagation nudges the parameters to make the right token a little more likely to appear next. Doing that enough times and it learns grammar, facts, and reasoning patterns. To actually feel the scale, GPT-3's training text would take a human over 2,600 years to read non-stop, and the computer equals 100 million plus years of single CPU work. Only possible with thousands of GPUs in parallel. Now, why you care? This single fact that it predicts plausible text, it doesn't look up truth, explains hallucination. And it's the root of almost every design decision that you take later. The second thing is it's probabilistic. And the only knob you'll really use, same input, different output. That's not a bug. It's the nature of the model. You control the randomness with temperature, which sharpens or flattens the probability distribution before sampling for the response that we talked about. When we say temperature is 0, it's greedy, it's effectively deterministic, SQL generation, data extraction, classification. So anywhere you want no surprises. When it's T, almost approximately 0.2 to 0.4, it's factual Q&A, summarization. So a little randomness will be there. And when T is approximately 0.7 to 1, it's used for journal chat, drafting, which is balanced. When T increases than 1, it's creative, brainstorming, more surprising, less coherent. And let me be honest about other knobs, because people overthink them, that we have top P as a nucleus sampling is the one that actually is a real alternative to temperature. So you sample from the smallest set of tokens whose probability adds up to P. The standard advice is to tune one of these knobs, either temperature or top P, and not both. There are other parameters like top K and the frequency or presence penalty exists, but in real production apps, they are rarely touched. So the parameters you'll actually set are going to be mostly temperature or max tokens. And sometimes a stop sequence also if you hit a max limit. So if you've never tuned top K, I'd say you're not missing much. It's fine. Here's something that surprises people, that LLM are bad at counting letters and doing math. And it's actually not a bug to fix for us. It's baked into how they have worked and how they have been trained. And two reasons. First, the model never sees letters. Before it reads your text, the text gets chopped into chunks called tokens. So strawberry isn't S, T, R, A, W and all of those characters to the model. It's more like ST plus RAW plus berry. So the individual R's are hidden inside those chunks. So how many R's in strawberry? Is genuinely hard for it to deduce. And it never saw them as separate letters. And the second reason is there is no calculator inside. The model doesn't actually compute. It recognizes from patterns. Now it's seen 2 plus 2 maybe million times, so it knows it's 4. But if you ask it 3847 into 9261, it's never seen that exact problem. So it guesses digit by digit with nothing tracking the carry. And of course, it slips. So don't make the model do what it's bad at. Hand it a tool. And this is the whole origin of tool use. So let it write code. It writes Python code, runs it, gets the exact answer, and always works. This is the real fix. Make it think step by step. Writing the steps out gives it a scratch pad to show its work. And that helps a lot for understanding those patterns. Make it spell things out, like for counting, have it write STRA, all those characters first and then count. Now the letters are visible to the model. And you can look it up, RAG, for exact facts. Fetch the real value instead of trusting any fuzzy memory. And now why you care? That instinct, the model is bad at this, so I'll give it a 2, is exactly the engineering judgment we need on those systems. Spotting what the model shouldn't be doing is half the job for us. Okay, now we can move to part 2, under the hood, how it actually works, and I'm excited about it. Before transformers, models like RNNs or LSTMs read text word by word in sequence, which is slow and bad at long-range context. Because by the time you reach the end, you have half forgotten the start. And then in 2017, Attention is All You Need came by Google, the paper that stated all of this. And that was the breakthrough. Read the entire input at once in parallel and let every token decide how much to care every other token. That mechanism is attention, and that's why GPUs love transformer. In plain terms, is just answers one question for each token. How much should I care about every other token? Each token produces 3 vectors, a query, a key, and a value. So a query is what I am looking for. A key is what I offer to be matched against, and a value is what I actually pass on. You take the dot product of query and key to get a value, which is the relevance score. Now on that, softmax the scores into weights, and the output is the weighted sum of these values. So the intuition I like is the river bank was steep, and the token bank scores highly against river. So it borrows from river's value, and its meaning shift towards river bank and not the financial bank. This is all in one parallel path. Now what is self-attention? Just means that the Q, K, and V all come from the same sequence. So every token is going to attend to every other token in the same input. It's the default which is inside every transformer layer. And it's the layer that actually captures about the verb agreement, pronoun preferences, topic shifts. When we come to multi-head attention, it runs the process several times in parallel, and each head with its own learned projections. And why it matters to have multi-head, then one head can track the syntax, like subject to verb, another head can track the semantics, synonyms, and another head can track another co-reference like he to John simultaneously. So 3 things simultaneously, so 3 heads are there. So a single head could only catch one pattern at a time, and that's why multi-head attention, which parallel heads are there. So we have all heard of managing context. LLM can attend to enough context window. But why? And attention compares every token with every other token. So the cost grows with the square of the length, which is order of n square. If you have 1k tokens, it's a million pairs, which is trivial. If you have 100k token, it's 10 billion pairs, which is second of compute. And that's the context window problem. That's the derivation of it. Now, it gets worse at generation time because LLMs generates one token at a time. And so to produce token number, let's say 500, so the model needs attention over all 499 before it. Naively, it would recompute the key and value vectors for every previous token on every step. That is exactly pure wastage of work. That is why we have KV cache as the fix, which is memory. Compute each token's key and value once and store them in GPU memory. And so on each new step, only compute the new token's vector and reuse the rest. It turns per step recompute from order of n square into order of n at the cost of holding all those KV tensors in memory. Hold that about memory cost because it's going to come back in part 3 that we are going to discuss now. The part 3 is what makes them actually useful and going a bit deeper on that one. Why LLMs are actually helpful. So there is terms called like RLHF and DPO. Raw pre-training gives a model that can predict text, not one that helps you. So ask a raw model a question and it might just reply with more questions because all it learned to do is continue a pattern. The magic of conversational AI actually comes from RLHF, reinforcement learning from human feedback. And it comes in 3 moves. So the first is SFT, which is fine-tune the base model on high quality human written examples to get an instruction follower. The second thing is the reward model. You show humans 2 responses. They pick the one that they like, the better one. You train a model to predict that preference. And then comes the DPO, which use the reward model to further train the LLM with RL, with a penalty so it doesn't drift too far from the SFT baseline that we have set. And this is exactly why models refuse harmful requests. Raters flag those low, and why a support bot can stay on brand. The stat is actually interesting that OpenAI's InstructGPT showed an RLHF tuned model was preferred by humans 77% of the time over a model which is 100 times larger without it. The size alone doesn't make a good assistant, and that's the proof. So what is then DPO? DPO is modern shortcut, I'd say. It reaches the same goal but skips the separate reward model building step and that finicky IL loop. So optimizing directly on preference data with a clean loss function. It's much more stable and cheaper, which is why most open source models actually use it. And so the practical rule is to start with DPO, only reach for RLHF and DPO if you need that top tier alignment, and you have the infra team to actually babysit it. Now fine tuning versus RAG. And the decision rule that saves you is always start with prompting. Move down the spectrum only when there is a measurable gap where prompting can't close. So you have the data and you can run the training. RAG adds that knowledge at inference time, no training, which is best for factual grounding and anytime that changes. Fine-tuning, on the other hand, bakes in behavior, style, or capability. It's not RAG or fine-tuning. Production systems often do both. A fine-tuned model with RAG for current facts. So when you fine-tune, you almost never touch the whole model itself. It's expensive. And it can make the model forget what it already knew. That is called catastrophic forgetting. So the standard trick is LoRA. Freeze the giant model and train 2 matrices on the side whose product is going to nudge its behavior. So you are updating well under, say, 1 to 5% of the weights. And because the original stays frozen, the model keeps its journal smartness with it. This is cheap, fast, reversible, and state-of-the-art for most tasks. And then we have QLoRA, which is quantized LoRa, which goes further. Shrink the base to 4-bit and you can fine-tune a 70 billion model on a single GPU. And I've got a whole separate video on LoRa and QLoRA to go a bit deeper on how they actually work and when fine-tuning actually beats RAG. It's the PubMed bird or the legal bird, if you have heard of. Why you care about this? So you start with prompting, you add RAG for knowledge, and fine-tune only for behavior is a real interview answer and a real architecture decision. And a bit deeper for AI infra interviews, know it exists and then go deep if that's your target. KV cache alone isn't enough because memory grows linearly. At a 100K context, the KV cache can be tens of GB per request. And at high concurrency, this becomes a bottleneck. So the fix is share KV across attention heads. So we talked about multi-heads attention. You have multi-query attention. All heads are going to share 1K and 1B. Cache shrinks by a factor of h with a slight quality drop. Then you have grouped query attention, which is like groups of heads share K and B. And the middle ground, this is the middle ground and it matches full attention quality. Llama 3 70 billion uses 64 query heads, but only 8 KV heads and 8 times cache reduction. This is the default in modern open models. Now there is something called as positional encoding and why it's even needed. Attention is permutation invariant. Attention has a blind spot on its own. It has no sense of order. So without a position signal, cat, sat, mat, and mat, sat, cat will look identical. So we need to inject order. Now rotary is what is used. It does it by rotating each word's vector by an angle based on where it sits in the sentence, like clock hands pointing to different times. So words near each other are rotated by similar amounts, words far apart very differently. So when the model compares two words, how far apart they are falls right out of the difference in rotation. Now the bonus is it stretches to longer text than it was trained on without breaking. Then there is ALiBi. It's even lazier and it's a complement. It doesn't encode position at all. It just adds a small penalty that grows with distance. So each word pays a little less attention to words that are far away. Dead simple and great at handling text larger than it is trained on. We have covered a lot and that's the bar. If you can reason about how the model behaves, where it fails and the trade-offs, probabilistic output, bad at math, so give it tools, finite context, so manage it, prompting before even fine-tuning or RAG, and you know now enough to build well and hold to your own in an interview. And the deep KV cache and positional encoding stuff is for AI infrastructure roles usually, and for AI engineering, knowing it exists is plenty enough.
If you take one thing from this, I hope it makes the next interview or the next thing you build a little less intimidating. Tell me in the comment what is still hard or what you want covered next. That's where I get my best ideas. And like if it helped, subscribe for the rest of the series and I'll see you in the next one.